Are we all still here? I know I sent an announcement out, said, uh, what, like 7:45, but they canceled the warning early, I guess. Okay, cool. Um, yeah. Well, that was fun. Most exciting review session I've had in a little while. Um, it's just raining pretty hard here. Everything seems fine, but when like five different notifications blow up on your phone that you need to get into a basement, I think that we should just do that, right? So, where was I? We were almost finished with this problem. Okay. We were trying to figure out the molarity of our CaOH2 solution, and we had almost finished. So I was just going to solve for the moles at this point, and then I can divide that by the volume of my solution. To find the moles here, I'm just going to plug in for the math we just did. 125 divided by 1,000, and then times 1.5, and then divided by 2. And that's going to give me 0. Sorry. That'll give me 0.09375 moles of calcium hydroxide. Now we're going to take that value and divide by the volume of my calcium hydroxide solution. To use that volume correctly, we're going to have to convert this into liters. There are 1 liter for every 1,000 milliliters. Milliliters will cancel with milliliters, and that's going to give me 0.050 liters. The final step here is to take that number of moles, 0.09375 moles, and we're going to divide that by the 0.050 liters. And that should give me my new molarity. So my molarity, therefore, is 1.875 capital M. I know there was a little bit of a pause in the middle of me solving this problem. Do we have any questions about it? No? Everybody good? Okay. Okay. That was just the all clear signal coming through. I saw that there was another problem that had been dropped into the chat.
A follow-up question
Yes,
to
sir.
this problem. In some instances, they ask for like limiting factor. How do you know which reactant is a limiting factor?
That wouldn't be related to this problem at all. The
Okay.
limiting reagent is specifically when you're doing a reaction and you're given two quantities of substance. In this particular case, what's happened is I was told that we have used a specific quantity of one substance, and then the point where it titrates the other substance, that means that the number of moles exactly cancel each other out. That's how these problems work. That's what a titration is. You're setting moles of one thing equal to moles of the other thing.
Okay.
Limiting reagent problems are a little bit different. And I imagine that this one is going to answer that question for you. So, I think I already did this other one, right? Yes. Let's go ahead and try this one, unless there were questions related to this titration one. Okay, great. Let's get into this new one. We have 4 ammonias and 5 oxygens react to make 4 nitric oxides and 6 waters. If 20 grams of ammonia reacts with 25 grams of oxygen, how many grams of the excess reactant remain after the reaction is complete? To solve a problem like this, we need to set up two parallel reactions. We will solve for both of them, converting them into one of our products. Whichever reactant makes less product, that's the one that's going to be our limiting reagent, and it's the one that will determine the maximum amount or the theoretical yield of the products we can obtain. Now, this problem is a little bit of a twist on that idea. It specifically asks for the grams of the excess reactant. So we'll go over the difference between finding the theoretical yield of a product and the grams of excess reactant after we do the first part. To begin, you're just going to set up two parallel dimensional analysis problems. So we'll start with 0.00 grams of NH3, and at the same time, I like to put the other substance down here, keeping in mind we want the number, the unit, and the chemical identity for both of these. Now, I'm going to multiply each of these by their molar masses to find the number of moles. I assume it's still more all clears coming in. Yes, okay. To do that, we need the molar mass of ammonia. Nitrogen has a molar mass of 14.01, and each hydrogen is 1.008 times 3. So we'll add all those together. I'm just going to be lazy and call it 17 grams per mole here, in the interest of saving some time. And then for the oxygen, we'll do the same thing. It's going to be 16 times 2, and that's going to give me 32 grams per mole for the oxygen. We want to keep in mind that we need the chemical identity attached to each of these, and so let me rewrite that with the chemical identity, grams of NH3 per 1 mole of NH3. So I'll use that term here. I want moles on the top so that I can cancel the grams on the bottom. Similarly for my oxygen, moles on the top so that I can put grams on the bottom to make it cancel. So grams of O2 cancels with grams of O2, and grams of ammonia cancels with grams of ammonia. I'm now multiplying both of these terms by something to convert them into one of my two products. In cases where you are asked for the theoretical yield of a particular product, you should set up a mole ratio from your reactant to that particular product. Remember that in order to determine our limiting reagent successfully, we have to convert both of these substances into the same product. If you convert them into two different products, you can't really compare apples to apples. In this particular case, because we've asked for the grams of the excess reactant remaining, we don't need to know which product is the what the mass of any of the products are, but it's just helpful to choose one and turn it into moles of that thing so you can very plainly see which of these reactants is limiting. So I'll just use the 4 NOs here. So I need a mole ratio that's going to make moles of ammonia cancel. I look at my balanced chemical equation and I find 4 ammonias here and 4 NOs there. So I'll write this as 4 moles of NO per 4 moles of NH3. My moles of NH3 cancels with the moles of NH3. Down here, choosing the same product, 4 moles of NO per, and this time it's 5 moles of O2. Now I have to, actually, no, I don't have to. Now, in this case, since we don't need to know the number of grams, I can just solve for these and compare the amount of moles to each other. So to do that, we'll take the 20 divided by 17, and then times 4 divided by 4 is going to give me 1.17. moles of NO. And then I'll do the same process for the 25 grams of oxygen. 25 divided by 32, and then times 4, and then divided by 5. And that gives me 0.625. That, of course, is moles of NO. And so whichever one of these gave us less product is the limiting reagent. So oxygen is our limiting reagent here. Because of that, I'm going to do the next part of the calculation using oxygen. Now, if you've taken this class before, or if you're particularly mathematically savvy, many of you could probably imagine a way that's faster than what I'm going to do here. However, I'm just going to show you the most foolproof way to make sure you arrive at the correct conclusion. You want to start from whatever your limiting reagent was and convert it into the other reagent. We're looking for grams of the excess reagent remaining at the end. So I need to figure out how many grams of oxygen were consumed in this process. Not oxygen, the ammonia. So to find the grams of ammonia consumed, I'll start from 25 grams of oxygen. I'll multiply it by the molar mass of oxygen. That allows the grams of oxygen to cancel. Now I multiply by the mole ratio between my two substances. I'm looking for ammonia, so I put 4NH3. And on the bottom, I'll put the 5 moles of O2. Almost forgot moles on the top. Don't want to do that. And I don't know why that happens sometimes. There we go. So moles of O2 will cancel with moles of O2. Now I know how many moles of ammonia we have. That is our excess reactant. Because I need to figure out the grams of the excess reactant, I'm going to multiply my moles of ammonia by the molar mass of ammonia, which conveniently we've already calculated up here. So we know that there are 17 grams of ammonia for every 1 mole of ammonia. So NH3 moles cancels with moles of NH3, and now we just have grams of ammonia left. So solving for this, we get 25 divided by 32 times 4 divided by 5 times 17. It's going to give me 10.625, and that should be grams of NH3. Whichever unit you haven't canceled out is the unit of your answer. Now, that's not the final answer here. We were asked for grams of excess reactant remaining. So we have to subtract the amount we actually used from the amount that we started with. To finish this off, 20 grams of NH3 minus 10.625 grams of NH3 is equal to our final answer. 20 minus 10.625 gives me 9.375 grams of NH3 remaining. Any questions on this guy? The one I gave you on your exam is considerably shorter than this. I don't make you go through and find the excess reagent remaining. I think that's the hardest version of this. Instead, I just ask you for the theoretical yield. And don't worry, there's only one of these per the exam. No questions? Everybody good?
So, with the theoretical yield for this question, it would be the 1.17 moles?
No. This value does not happen. It's imaginary. We did 2 checks, right? We checked to see if this was the limiting reagent, and we checked to see if that was the limiting reagent. The end result told us that because the oxygen produced less moles of nitric oxide, this oxygen is the limiting reagent. And so all of this effectively doesn't happen. It's a lie. It's an exercise that we do to try and figure out which thing makes less stuff for us. To kind of oversimplify the concept, imagine you're trying to make grilled cheese sandwiches for a party. You're given 5 pieces of cheese and 20 slices of bread. If you know that you need 2 slices of bread and 1 slice of cheese to make 1 grilled cheese sandwich, the math works out that you're only able to make 5 grilled cheeses because you run out of cheese first. So there's 5 slices of cheese, you can make 5 grilled cheese sandwiches. Doesn't matter how much bread you have. The bread is the excess here. You could have 10 slices of bread or you could have a million slices of bread. You're still limited by the quantity of cheese. That's what happens here. We didn't need this equation anymore. This doesn't actually happen. We know now that we have more ammonia than we need, and so we focus on this for the remainder of the question. So you would say maybe that this was the theoretical yield of nitric oxide, but they didn't ask us for the theoretical yield. We were asked for grams of the excess remaining. And so this was just kind of an intermediate step to eventually solving the amount of ammonia remaining.
Okay.
Good question. Any others on this problem? Okay. Any other questions in particular that you all would like to work on? Okay.
Question regarding enthalpy.
Okay. Not on this exam, but happy to
Enthalpy is
answer
not
it
an
anyway.
exam.
Yeah.
Oh, okay. Okay. All right, then I'll
Y-
deal with that later.
Okay, great. Yeah, you should definitely refer to the study guide that I posted for this exam. That contains all of the topics you might be tested on. So if it doesn't show up on this list, you will not be tested on it.
Okay.
Okay. I want to do some practice determining oxidation numbers. Maybe that's trivially easy for all of you, but I always struggled with it when I was an undergrad. So if we're given something like Na2CO3, how do we determine the oxidation number of a single element in this compound? For some elements, the oxidation number is given by a rule. For example, metallic cations will always have the same oxidation number as their charge. If the charge of sodium is a positive charge, then we can assume that the sodiums in this molecule will have a +1 oxidation number. Oxygen is another one of those that has a rule that determines what its oxidation number is. Because oxygen is so electronegative, it's pretty much always going to make a -2 charge. Carbon, on the other hand, if you look at the rules, well, it doesn't have a dedicated rule, which means that you will sometimes need to calculate for the charge of your unknown element by looking at the oxidation numbers of everything else. The approach I like to use to do that is I take each of these values, so I'll use an X as a stand-in for carbon's oxidation number, and if you take the oxidation number for each and multiply it by the subscript, or the number of those elements, that's going to allow you to set those all equal to the charge of your compound. So this would be the charge. And that allows you to find the missing variable. If there is no charge shown, that means that the charge is equal to 0. So we'll set this equation equal to 0 to start. I'll take 1 times 2, that gives me 2 from the sodium, plus x times an implied 1 here, and so x, and then -2 times the 3 here, that's going to give me a -6. When I rearrange and solve, I would find that x is equal to +4. That is the oxidation number of carbon. Any questions on this one?
Are we going to be given a list of the oxidation rules?
No.
Okay.
They're short. There's like pure elements are 0. Metallic cations are the same as their charge. Oxygen is -2. The halogens are -1. That's the whole list you need to know. Other questions?
What will we be given on the exam?
Polyatomic ions, periodic table.
Okay, thank you.
Yep. Oh, and I think there's a solubility rules question, and I gave you the solubility rules inside that question. Other questions?
This is just like general. Everything that is like on the study guide, do you also have videos about those posted like on your YouTube that like we could go watch?
No. No, I don't. Tend to record a bunch of videos for different topics. I'm sure you could find videos for each of those topics. There's a bunch of YouTube creators out there. But typically speaking, the only content I host on my YouTube channel is review sessions. You can find old review sessions from previous classes. There might be some problems contained there. And then you'll also find like specific instructions for like how to take the exam, stuff like that. But that's the only kind of content I post.
Are there any other specific resources that you think would work best for studying in this? I think Khan Academy was one that we've done before.
Yeah, Khan Academy is pretty good. I know the guy that made those videos, and I think that he is an excellent instructor. Really, any YouTube creator is going to be able to make pretty good YouTube videos. Just look for something that has a high view count, and I'm sure that it'll be instructive for you. I definitely recommend timing yourself when you're studying for this test. Like pull together a couple of homework questions that you found challenging and see how long it takes you. I'm pretty sure there are 5 math problems on the test. That's what I wrote here, and I don't know why I would write that if it were a lie. And so, maybe get 5 of the hardest math problems you can find from the homeworks and see how long it takes you to do them. And if it takes you less than an hour, then you're probably in pretty good shape because we have a full 2 hours to take this test. If you find that you're only like halfway through them after the hour is gone, then you definitely need to get better at solving those types of problems quickly. The best way to do that is through repetition. So just like change the numbers, solve it again, change the numbers, solve it again. There's only so many ways we can ask the same type of question, and so eventually it should get pretty routine for you. What other questions might you have?
Could you give an example for the type of question that'll be which is being oxidized and reduced?
Yeah, sure. So this type of question ties in very neatly with the classifying chemical reactions topic. Oxidation is loss of electrons, and reduction is gain of electrons. This symbol, the E with the superscripted minus sign, that is the symbol for the electron. The reason we write it like this is because it's a neat little mnemonic device. We say oil rig to remember oxidation is loss, reduction is gain. The other way you can remember that reduction is the gain of electrons is that negative oxidation numbers match negative charge of the electron. And so if something is being reduced, you are decreasing the overall oxidation number of it. Let's take a look at an example. So if I took some sodium metal and I combined it with some chlorine gas, I would make 2 sodium chloride. We need to evaluate what the oxidation numbers are for these elements before the reaction and after the reaction in order to determine which is oxidized and which is reduced. The oxidation number of any pure element is equal to 0. So I'm just going to put those oxidation numbers as zeros over those elements to help keep track. Then I'm going to go ahead and look at the other elements on the product side and figure out what their oxidation numbers are. Remember that the monatomic cations, like for sodium here, they're going to have the same oxidation number as their charge. Because sodium is in that first group of the periodic table, we anticipate it'll make a +1 oxidation number. Then the chloride, now that one is one of the rules that we have. All of the halogens make a -1 oxidation number, and so this will be -1. Since oxidation is a loss of electrons, we expect oxidation numbers to increase when that element is oxidized. So sodium went from a 0 to a +1. I would say sodium was oxidized here. Chlorine is therefore reduced because we went from a 0 to a -1. It had to gain an electron for that to happen. So you would say sodium is oxidized, and the chlorine is reduced.
Thank you.
Of course. This is a very helpful approach if you're trying to determine what classification a reaction might have, like especially if you're like stuck on something or you're pretty sure there's at least 2 types. You might say have something like C2H6 plus O2 reacts to produce CO2 plus H2O. This is a combustion reaction, but the question might involve many different types of reaction classification, so you would need to know, is this also redox? Is this also precipitation? Stuff like that. In order to figure that out, we're going to assign oxidation numbers to each of these elements. Hydrogen is always a +1 because it's in group 1 of the periodic table. There are 6 hydrogens, so we'll give this a +6. My carbon's got an X here, and so we'll set that equal to 0. 2x plus 6 is equal to 0. X is therefore equal to 3. And so that means that carbon has a -3, sorry, it should be -3, -3 oxidation number. Oxygen here is a 0. And then we can evaluate the carbon and oxygen on the other side. So when oxygen is attached to anything other than itself, it's going to get a -2. And so then the carbon here is going to be based off of oxygen's oxidation number. Because it was -2 times 2 here, that gives me a -4 for the oxygen. If I set that equal to 0, that means that X must be a +4. And so without needing to go through the whole rigmarole of what's oxidized and what's reduced, we have clear evidence that a redox reaction has occurred. We know it's redox because we went from having a pure element with a 0 oxidation number to the oxygen having a -2. And so that means it had to be redox. Other questions? Other topics?
A combustion analysis?
Sure, I can try and find a combustion analysis problem. These are unfortunately really challenging to make up because the ratios have to work out perfectly or you get a nonsense value. Let's try this guy. We have a 1.5 gram sample of a hydrocarbon undergoes complete combustion to produce 4.40 grams of CO2 and 2.70 grams of H2O. What is the empirical formula? Pretty much anytime you're doing anything with stoichiometry, you're given grams, you're given moles, you're given different compounds, the first thing you should think is, how do I set up this dimensional analysis problem? Students that did dimensional analysis on test 1 scored very, very highly. Students that tried to do other mathematical approaches, let's call it, didn't actually do quite so well. So please make sure you're trying to set these problems up in the exact same way that I do. In particular here, to find the empirical formula of something, it's going to be in the format of CXHY because we have a hydrocarbon, just hydrogen and carbon here. So I need to figure out how many moles of carbon there are and how many moles of hydrogen there are in the initial starting material. The way we do that is by looking at the products. So we've been given, let's see here, 4.40 grams of CO2 and 2.70 grams of H2O. We're going to multiply these by their molar masses. The molar mass of carbon dioxide, it's going to be 12 plus 16 plus 16, and that's going to be 44 grams per mole. So we'll put 1 mole on the top and 44 grams on the bottom. For my H2O, it's 18 grams per mole, more or less. And so we'll have 1 mole of H2O on the top and 18 grams of H2O on the bottom. Now, grams of CO2 cancel with grams of CO2, and grams of H2O would cancel with grams of H2O. Now I'm going to multiply these by something else to end up at X and Y. So X and Y are the numbers of those atoms contained within my starting material. So for every 1 mole of H2O, notice that there are 2 hydrogens there. And so I'll write a mole ratio where there are 2 hydrogens for every 1 H2O. Similarly here, CO2 just has the 1 carbon, so I'll say that there's 1 carbon for every 1 CO2. Then I can just go ahead and solve. So the CO2 will cancel, the H2O will cancel. That'll tell me how many moles of carbon and moles of hydrogen I have in these 2 reactants. So heading over to the calculator, or I guess I don't really need to for the first part here, 4.4 divided by 44 is going to give me 0.1. And then the 2.7 and 18, I feel like that's 2/3 or something like that, but it's late at night. 2.7 divided by, what was it? 18. Yeah, I was pretty far off. 0.15. Now what we're going to do is we're going to plug those values in for our X and for our Y in this empirical formula. So C 0.1 and H 0.15. Hopefully we remember from our earliest unit in this class that you cannot have partial atoms, right? The whole thesis behind atoms is this is the smallest collection of mass that behaves in a predictable way. All of the carbons behave like carbon, all the hydrogens behave like hydrogen, and if you cut it apart, it's no longer those elements. So we're not allowed to have decimals here. The way we can fix that, since an empirical formula is just the lowest whole number ratio, we'll divide both of these by the smallest number. In this case, that's 0.1. And so that's going to give me C1 H 1.5. We're closer to the final answer, but I do still notice that pesky decimal place that the hydrogen has. In this case, we can simply multiply by some factor that'll make the 0.5 go away. The simplest one to use is 2. And so by multiplying 1 by 2 and the 1.5 times 2, we end up at C2H3 as the lowest whole number ratio, or in other words, the empirical formula. And then in the part where it asks you about the molecular formula, don't worry about it. I didn't put it on the test. Any questions on this type of problem? Okay. What other stuff would you all like to cover? Okay. Hopefully that means you're feeling relatively confident. I would encourage you to try and sign up for those one-on-one, graded conversations that we're doing. They're not actually going to be graded. Instead, I'm just going to be giving out 5 bonus points on the exam. And it's 5 points to the overall test grade, not 5%. I think I made it out of 80 points this time. So 5 points is actually more than 5%. I think it's a pretty good deal, and it gives you opportunities to study a little bit more. So if you didn't show up today super prepared with questions, you might find something while you're studying. Please go through and sign up. I'd love to meet with you all independently. I am also going to post these recordings to my YouTube channel if they worked out. I think they should be okay. And otherwise, I'm ready to call it a night unless there's any last minute questions. Everybody good? Awesome. All right. Well, I'm very sorry again for that weird interruption we had in the middle there. Hopefully you found this instructive anyway. And I look forward to any questions you might have and helping you study as you prepare for exam 2. Take care and have a great rest of your night, guys.
Thanks. You